To the continuation of Mitch Luskin's lecture series and on electronic density of states and transport properties.
Okay, so I'm going to kind of review a little bit where we were last time, and then we'll move on. So recall what we're trying to do is to compute. In this lecture, we're trying to model and then compute the electronic density of states of a stacked 2D multi-layer structure. Okay, and so here, recall, we have four different existing 2D elements, all stacked one on another. The two graphene layers are rotated with respect to each other. And this is just a top view, and the key thing here is that although each individual layer is periodic, when you stack the two, they're no longer periodic. Now, of course, in a bulk crystal, you stack 2D periodic structures, and you get a periodic structure. Okay, but here because of the mismatch in lattice parameter or the rotation, we actually have a non-periodic, aperiodic structure called incommensurate. Okay, so we're just going to focus in this lecture on bilayer systems, although much of our theory extends to multi-layers, and that's actually a topic of a lot of our current research, is to extend a lot of this to multi-layers. But okay, so we'll focus here on bilayer, and so we can describe the lattice of each individual layer, j is equal to 1 and 2, by script r sub j, right? Just an invertible matrix times z2, okay? And then each individual sheet has its own unit cell, okay? It's just the span of your two basis vectors where the coefficients are between 0 and 1. Okay, and each individual sheet, is periodic, okay, but the combined system is not periodic. Okay, now, so I'm going to describe so the union of these, this is really going to be the structure we're going to look at. Now, okay, remember, and so it's not, and we're not looking at, there actually is a distance z between each layer. But that's not going to be important in what I do. That's like a hidden parameter, because it's all hidden in these tight binding coefficients. So anyway, so we can just look at it here as simply something in the plane, the union of two lattices. And again, recall, we have script A and script B represent the orbitals, or the degrees of freedom associated with each lattice point. Okay. Now, okay, so then, so recall we saw this picture last time, and this is just a 2D lattice, hexagonal lattice, rotated and placed on another. Okay, so we have the lattice points red and the lattice points blue, and so what we see is we see a larger scale structure, which is called the Moray scale. Okay, and I'll talk about that later. So the Moray scale is essentially where the system is almost periodic, okay? So there's kind of a repeating, so in some sense this, so as we go from point to point, as we really go through the different, say, red points, we see the position of the upper lattice, the blue lattice, is different as we go from point to point, and that's characterized by a vector B, a shift vector, or sometimes called a disregistry. Okay, and so intuitively, I stated last time that there's a one-to-one correspondence between the points in real space blue, okay, and the shift with respect to the other lattice, or vice versa. Okay, so you can characterize essentially the state of your system by real space or configuration space. Okay. Now, so what is it? okay, so I keep throwing this word incommensurate around, and so what really is incommensurate? And it's a little different than what I described last time. What I described last time is I said, okay, as I go from point to point and I look around, the environment is different at every point. It's uniquely different, right? Where I'm sitting at a red atom, and I say, where is the relative vector to the nearest green atom? That's different as I go from red atom to red atom, okay? But now, in fact, the result we really need, what it says, in fact, is that that picture needs to be true for the reciprocal lattice, okay? So if I graph the reciprocal lattice, right, we define the reciprocal lattice, it's just the conjugate lattice, okay? So the conjugate lattice has the property that each point has a unique environment. So this is the one way to write down that precise property is what's incommensurate. Now, there's really pathological examples where a lattice and its reciprocal lattice, like the lattice is incommensurate, but the reciprocal lattice is not. Okay, but generally this is true for both the lattice and the reciprocal lattice, and you might as well just go ahead and think about that if you want. But in fact, in the main theorem we use this result. Okay. So, so just for simplicity, P sub j is just going to be a transposition of 1 and 2. So it's just a nice, so I get to, with this notation, I can kind of talk about both layer 1 and layer 2 in one simple formula. But, so this theorem here, this actually is, I would say, the fundamental theorem behind all the theories I'm going to talk about. For density of states, conductivity, mechanical relaxation, okay, mechanical properties. This is the main theorem. So, so what does this say? It says that if I give you a function h, and so let's for simplicity, let's let j equal 1. It's easier to talk about. Okay, so j is equal to 1. So I have a function h that's periodic on the unit cell of lattice 2, okay? So remember, so we have a lattice, let's say if it's just hexagon and rotated hexagon, we have a unit cell, and then we have the unit cell in the layer above is rotated. So the function is, so h is periodic, right, with respect to the structure of lattice 2. Think of it that way, okay? And now, but now I want to sum h at the lattice points of lattice 1. So I sum a function on the lattice points of layer 1, but the function itself is periodic with respect to the other lattice. Okay. Now, then what we can prove, and it's in our papers, I'll mention it, it's a one-page proof, as you let the ball R get larger and larger, this converges, right, this simply says that sampling over lattice 1, right, a function that's periodic on lattice 2 is simply the same thing as averaging the potential over all possible values B, right, or shifts or dysregistries over that unit cell of lattice 2. Okay, so that's, I'm packing a lot into that little simple statement, but let's go back here. Okay, it just says that, it says, okay, I have a function, let's say that's periodic, right, with respect to lattice, the blue lattice. Okay, I have a function that's periodic with respect to the blue lattice. Now that function, of course, could be the effect of the blue lattice, like electric potential or the mechanical effect or something like that. So a function is periodic with respect to the blue lattice. Okay, but now I want to sample with respect to the red lattice. Okay, and as all I'm saying is what I could do is just simply just kind of pretend my red I could just say take the red atom to be here, and then just integrate over the function where the blue lattice takes any value in this rhombohedron figure. Okay, so so remember, it's the same thing of going over the whole real space domain and sampling that function at all the red lattice points. The same, I can achieve the same effect simply by holding the red point fixed, say at the origin, and then letting the blue points just uniformly span this the lattice of the blue. Uniformly scan the unit cell of the blue lattice. Okay, so it's okay. So that means is I can actually, rather than do a kind of a large body limit, go sample everything out to infinity, I simply can just sit at one point and just move that second lattice around, okay, with respect to its unit cell. Okay, so what that means is, okay, whatever it is, this could be, if I'm trying to derive an elastic energy, for instance, it says that H might be what's called a site energy, okay? H is a site energy. It's just the mechanical energy of a lattice point. That depends on the position of the nearby points, okay? It could, or whatever it is, then if I take this large body limit, we want that to be our elastic energy, and that's what we'll do next at 4 p.m., okay? Then, okay, but what I really wanted to have was a continuum model. So I go over here and I can actually derive a continuum model. This allows me to pass from an atomistic to a continuum model. Okay? So, okay. All right, so let's, okay, so let me kind of develop our approach to density of states. So, okay, so recall that we have our basis functions phi, and they're just, and those were just achieved by translating to. We have one basis function for each alpha, and then phi of r alpha is achieved just by translating that basis function to all the other lattice points. Okay, and so we have r is the lattice points, alpha is that orbital, but. All you really need to know is these are just functions that are indexed by r from a lattice and alpha from a finite set. Okay, so at this point we can even forget the physical model underlying this. We simply have an operator that we can define by this it's called hopping function. Okay, so given our differential Schrodinger equation with our orbital basis functions, we can then derive an operator, right, on L2 of the lattice of the degrees of freedom. Okay, and then we have an oops, I forgot the eigenvalue. Okay, then we have an eigenvalue problem which should have a lambda here. Okay. And recall that last time we went through the traditional theory for periodic structures where H has translation symmetry, and in that case we could use Fourier transform methods. Okay, and then we could simply diagonalize the system. Here, H does not have translation symmetry, so we cannot diagonalize it by the block or the Fourier transform. Okay, so so the question is, what do we do? How can we solve this problem? Okay, now, so one of the key things in all that I do, we have to have some assumptions. So so the first assumption, and the main assumption, is that the Hamiltonian entries, the matrix, has some kind of exponential decay. So when you go off the diagonal, right, the elements are exponentially decaying. Okay, so remember, rather than thinking of matrices, we just think of our indices as given by lattice positions. So that just says that the H function, right, that describes the operator, right, is exponentially decaying, right. So the matrix element corresponding to two different positions in space is exponentially decaying as that distance starts increasing. And we also need exponential decay for higher derivatives too. But let me not write it all out. Okay, now, so let's get back to what we mean by density of states. So now, so omega, this is our full set of degrees of freedom, right? Now, the full set of degrees of freedom is infinite. Okay, we can't really deal with that directly. Okay, so we just take some finite subset of the total degrees of freedom, omega, we call it omega tilde, and suppose there are n elements in that reduced set of degrees of freedom. Okay, then we have a Hamiltonian, a kind of a projected Hamiltonian that just takes the elements, right, from our restricted set. Okay, so now we just have a matrix, an n by n matrix, and then we can define the density of states as I again described last time. I mean, density of states is what it is. You just line out, you put the eigenvalues on a line, and then you say, okay, the density is just a sum of the delta functions at the points, and we can define that weakly just by taking any continuous function g of the operator, take its trace, divide by n. So it's convenient for us to talk about density of states as in this weak form. So d of h tilde is the density. Okay, it's the density, and we apply the density to a function, right? Then it's like the sum of, I should have written this down, it's just the sum of g of the eigenvalues. Okay, so this is, and again, this is how we would normally compute the density of states. Okay. Okay, and think about g being if g is a delta function, this simply is, if g is the delta function at some energy, then this simply is the density of states. But of course, that's not really rigorous. We have to, so think of g as being some smooth Gaussian, then we get a smoothing of the density of states at the mean of the Gaussian. Okay, now, so what is the, so that's the density of states. We saw that last time we looked at graphene. Now, it's actually very important to think about what's called the local density of states. So the local density of states are simply the individual diagonal elements. So remember, so k corresponds to some lattice point. K corresponds to some lattice point or orbital, and simply that the kk element of this matrix is the local density. I mean, it really means that's the local density of the electronic charge at that point. Okay, so this is really a physically measurable quantity, the local density of states. Okay, and it's actually a very important quantity. Okay, now the total density of states, right, is simply achieved by summing over the local density of states. Okay, now here's another, this is like the key idea in our method, and this is where we sort of we kind of use that ergodic theorem that we talked about, right? This was the big ergodic theorem. Yeah, this is where I'm going to use this ergodic theorem to derive my method. So, so what I want to do is, so now I'm going to look at specialized finite domains. Those are just domains where we just have a kind of a cutout of radius r. Okay, and now what I want to do is, so I could look at sort of matrices H with some at a point, and I just include, and those matrices are obtained by just taking all the atoms within a distance r of a given atom, and I could go through each of those and compute a local density of states, at each point. But what I'm going to do is instead, rather than walk around to all those atoms in space and some crazy sampling, I'm going to do something very systematic. I'm just going to sit at the origin at one point, and I'm just going to shift say if I'm focusing on layer 1, I'm just going to shift layer 2, right, by B. And B is going to be in the unit cell of layer 1. So rather than travel around to every lattice point, I just stick at the origin, and I just move the lattice around me. Okay, so that matrix. This is that matrix. Okay, so this is hard to read. It's just simply when you shift. The R just means you're shifting the other sheet by a distance B. Okay. And now what we want to do is we simply want to take the diagonal. We want to go to that. We want to look at that matrix. Okay. And what do we want to do? We want to. Okay. First. Okay, here's that matrix H sub R. Okay, let's just say we haven't done any shifting, and now if I go and look at the diagonal element corresponding to some lattice point R, that morally should be the same as just as standing at the origin, and then taking the corresponding shift of R, and then shifting appropriately. So I'm going to reproduce the environment of lattice point R by standing at the origin and moving the lattice. Okay, so instead of walking over here, I shift. Okay, so it's like an ergodic theorem. Okay, so instead of walking somewhere, I'm just going to stand somewhere and just shift the whole lattice. Okay, so I think it's a reciprocal process. So what that means is simply what I can. Okay, so that means that again. So instead of looking at each of the, instead of looking at the diagonal element corresponding to each of these points here, right, I simply just stand at one point and just look at the shifts. Okay, so now, so this is going to be our method in a nutshell. Okay, so this is the density of states. This is what we want. Okay, this just says, here's H sub R, right? And what I want to do is I just want to sum the diagonal elements of H sub R, right? So I just, H sub little r, I just sum the diagonal elements, divide by the number of degrees of freedom, right? That's what I want to compute. Okay, now, so now what I want to do is I replace the diagonal element at R of H sub R by H sub R shifted. Okay, and now by the ergodicity, right? This here is essentially forget the G. This here corresponds to just shifting standing at the origin. Okay, so I can write this, so I can actually I can represent this sum over over some ball of radius r. Okay, I can represent it as some kind of discrete integral, and then when r goes to infinity, this becomes a continuous sampling over the unit cell, and so we'll be able to so this will give a rigorous proof. Right, this gives a rigorous proof of the convergence of the density of states. Okay, so and this really what it is. And the next theorem will rigorously tell you that this convergence is actually exponential. Okay, it's exponential. Okay, so we have so this is like we started on the problem, we didn't actually understand this. Okay, so recall, we have an incommensurate structure. We want to compute we want to know, does the density of states, okay, does it actually converge as the radius goes to infinity? So that's what we've been able to prove. Okay, and not only have we been able to prove, you're going to see that this actually lends itself to a very efficient numerical method that's exponentially convergent, as opposed to the naive approach, which is going to converge linearly. Okay, so the naive approach, of course, is is just to go and just to directly compute this, right? Go directly compute this. Take some large R and take R larger and larger, and then study the density of states. Okay, that's like the brute force method, and that approach converges linearly, but we'll be able to get an exponentially convergent method by using this representation. Okay, so let's so now to kind of be a little more precise, let's look at spectrum. So let's look at the so basically what we have here is so let me call S of H. It's like the it essentially is an interval in the real line that contains all the eigenvalues that are ever going to pop up in this problem. Okay, that's I think you probably all know about the spectrum of an operator, like what of a Hermitian operator. So I have all kinds of Hamiltonians running around with different radius. So I want to have an interval that contains all those eigenvalues. Okay, and then I'm going to focus at first on analytic functions that are analytic, right, on the spectrum. Okay, and then let's let d tilde be this kind of neighborhood of analyticity around the spectrum. Okay, you'll see where that pops up. Okay, so here's the. Let me just start in on some of our results, and I'll give a little very simplistic kind of proof of this. Okay, so what I claim is that those local density of states, okay, if I take a ball of radius r, if I cut off the Hamiltonian with a ball of radius r, then I claim that converges exponentially. I'll show you that in a minute. Okay, so it converges exponentially. It's a bounded operator. Okay, don't worry about that. Then here, this just describes precisely the exponential convergence of this local density of states, and it also describes the dependence on the test function on its analyticity. Okay, that also enters, of course. Okay, and then also we have this density of states is a function of that shift, and this just says, okay, as a function of the shift, we also have periodicity and smoothness. Okay, because remember, numerically, we're going to have to integrate that quadrature. We have to integrate over the Brion zone, so we're going to have to do a quadrature, and any kind of a convergence of a numerical method depends on the smoothness of the function we're approximating. Okay, so here's the big theorem. Okay, so this just says that. What does that say? This says. This says no shift. This simply is this is what I would characterize as simply that direct large body limit, and that says it converges to this. This is what I derived formally 2 slides earlier. It says, in fact, it does converge to this quantity. Okay, and the convergence is exponential. Okay, so this is. Yes, this says that in fact this problem does have a large body limit. We take the density of states does converge as r goes to infinity. Okay, and this just kind of shows you for the local density of states the kind of convergence that we get. Okay, so it just shows you even with r equal to 40, we've kind of reduced it by 5 orders of magnitude. Okay, and now, because I recall we had to do this quadrature. So instead of going over the large body limit, we just have to integrate over all these disregistries or shifts. Okay, so that's why we wanted to know about the smoothness of this function, and we can show that just with any kind of simple uniform discretization, we get a exponential convergence in the number of quadrature points. Okay. Okay, so now, so how do we do all this analysis? Okay, so all this analysis is, we use this very nice kind of representation of the local density of states given by the Cauchy integral formula. Okay, so so let's remember. So omega was our full all the lattice points on both layers, and omega tilde was a finite subset of that. Okay, and suppose again G is analytic here. Then, okay, so we were always interested in computing the trace element of G of H tilde, right? Sorry, of a diagonal element of G of H tilde, and we just chose K as a representative index. Okay, and just a direct kind of application of the Cauchy integral formula says we can actually represent it this way here. Okay. Okay. Now, in fact, this is, by the way, I kept talking about G of H, where G was some function, and we all know G of H, if G is a polynomial, then you just multiply H squared, H cubed. Okay, but in fact, this is also a way, just drop the KK. This is a way you can define analytic functions of operators just through this kind of Cauchy integral formula. Okay, so you can create this. Okay, so so then so the main and now what we want is right. We're assuming a property about the Hamiltonian matrix H. We're assuming that H is we're assuming that the Hamiltonian, the off-diagonal elements decay exponentially. Okay, and what we want to know, and so what we want, and we wanted to know all kinds of properties of the of these entries here, K here, and so what that means here is that we really need to know if H decays exponentially, does the resolvent decay exponentially? Okay. Now there's a whole kind of body of work called Coombe-Thomas decay estimates. Okay, and so that's what these Coombe-Thomas decay estimates say. They say that if H decays exponentially off the diagonal, then the off-diagonal elements of the resolvent also decay. Okay, so so let's so the version here I'm going to use we found in a paper by Chen and Ortner. Okay, so this is just so. Don't worry about all this other small print here, but okay, so it just says that, so here we have K and L, they can be your lattice points, and Y is some kind of deformation, but okay, so, or you can let Y of K be K. So that just says if if the off-diagonal elements of your matrix are decaying exponentially, right, as K minus L grows, then the off-diagonal elements of the resolvent also decay exponentially. Okay, so that's the that's the main Coombe-Thomas estimate that we need to prove everything. Okay, so now so how does that? So let me just so I'm just going to show you how this works. I mean, this stuff works even for a lattice. Okay, so let's just kind of work it out there. So let's suppose we have a 1D lattice. Let's just set the lattice constant be 1. Okay, let's just go and assume that the off-diagonal elements of some of your matrix decay exponentially. Let's also assume that the off-diagonal elements of the resolvent decay exponentially. Okay. Then let's let R prime be greater than R, and we want to compare the let's say these trace elements, right, for G of R prime and G of R. Okay, so remember the first, the main question we want to ask is does G of HR converge as R goes to infinity? Okay, so we just show that as R prime and R both get large, they're going to come exponentially close to each other. Okay, so So, so we just set it up. We set it up g of r prime minus g of hr, and we can then, we just use the Cauchy integral representation, okay? So what does that mean? That means we have to estimate the difference in the resolvents, okay? And so now we can just we can just write first we use the resolvent, we write the resolvent in terms of like this, and then we have to then work out the matrix elements. So in fact, this is what we get, okay? So we want remember, so we wanted the trace, the 0, 0 matrix element of the difference in the resolvents. And so what is that? That's so again, we just had, we wrote this as this here, forget the subscripts, and then now we have to carry out, then to get the 0, 0 element, we have to then work out all these sums, these products and sums. Okay, so what does that mean? I mean, this here says, okay, so if you look at this, right, this is going to be 0, right? If L and M both represent lattice points that whose radius is less than r, then this is going to be a 0 element. So this is only non-zero when L is, say, when L is greater than r and M is not greater than r, or vice versa. So there's only two possibilities where we can pick up non-zero elements, right? So if L and M, right, if L and M represent lattice points that are for which the radius, for which their distance, for which their magnitude is less than r, right, then this here is 0, okay, right? So we only have to, so that throws out all these, so that throws out everything but these terms, these sums, okay? And so now let's just look at one representative sum. So we look at this representative sum here, right? Here we say we're summing this product over L in omega r prime minus omega r. It means the magnitude of L is greater than r, okay, and M, the magnitude of M is less than r, so that means this guy is going to be non-zero. So in this case, all these guys are decaying exponentially, right? We put the exponential decay results that coming from the assumption and the Coombe-Tom's estimate into this, right? And then from that we simplify a little bit. When we convert it to an integral, we carry it out, and we get exponential decay in R. Okay, so this is telling me this whole notion of the local density of states for an incommensurate system is actually well defined. It's converging exponentially. Okay. Now, what else is important is, so what that means, now again, let's stay just with a simple 1D lattice, then in fact, we just showed, right, now in a lattice, right, the local density of states is the same as the density of states, because every point is the same, okay? And so we just showed that in the case of a lattice, just taking the forget about this local method, forget this trace thing, that we have an approximation. The local method converges exponentially to the trace of the full lattice. Okay, but now let's just say that you just went ahead and you did the brute force method, which says, okay, I'm just going to take the trace of g of r. Now the problem with g of hr. Now hr, remember, that had a truncation had a truncation of the matrix at r. So all the local stuff is really bad near the boundary. So you have boundary effects of okay. So this just says I actually then computed the error, right, for points that are close to the boundary, because when they're close to the boundary, right, we still had exponential decay, but now it's if we're at point s, then it's r minus s is the distance to the boundary. So it's effectively like a smaller little radius. So again, we do this integral. Anyway, bottom line is let's say the brute force direct method of just taking taking a large body limit only converges linearly, but when you use this local method, it's converging exponentially. Okay, so now we have so now let me talk a little bit about the numerical approach here, and so I think we've got something. Okay, so in the end, I think we have a very efficient numerical method. So if we go back to our method, what do we have to do to say let's say we just went brute force, and let's say I was even willing to use that this notion of the representation in terms of shift integral over the unit cell instead of all that large body sampling, but still I'm going to have to do an eigensolve on these Hamiltonians, right, with have a radius, for all the atoms within radius r. Okay, then we have to do that for each quadrature point. Now that's very expensive because computationally it scales like r to the sixth. Okay, for the amount of computational work to solve the eigenvalue problem, okay, goes like r to the sixth, right? Because remember we have right, in a ball of radius r, we have r squared degrees of freedom, right? In the eigenvalue problem scales like the cube of the number of unknowns. So we have r to the sixth work to solve each of these problems, and we just brute force did an eigensolve. Okay, so but what I'm gonna talk about is using essentially Chebyshev polynomial, something called the kernel polynomial method, and we're going to be able to reduce this to a scaling of r squared for each shift. Okay, and and then not only that. Okay, so let me show you how does that work. Well, what that works is that, remember, we want to compute the density of states. We really want to for that g, we'd like to use a delta function right at the energy. Okay. But now we represent the delta function in terms of Chebyshev polynomials. Okay, do a Chebyshev representation of the delta function. Here it is. So it's not quite Chebyshev. We have to do some modification of the coefficients to remove the Gibbs phenomenon. Then recall this is what we then have to, this is our computational object now. Okay, now eventually we have to replace H by a finite matrix. Okay, so then end of the day, the whole thing comes down to this. Okay, so for each shift B, we have to compute this. So what does that mean? End of the day, we only have to do. We have to essentially apply the Chebyshev polynomials to each shift. Now remember, applying the Chebyshev polynomials, we have the recursion relationship that makes that easy. That's an efficient evaluation. We use the recursion relation for Chebyshev recursion to make this efficient. Okay, and then once we've computed these quantities, then it's simple to actually evaluate. There's no more matrix vector work to evaluate at any other energy. Okay, so the magic of Chebyshev expansion enables us to avoid a direct eigensolve. Okay, and then so then what we end up doing is we had all these estimates, right? We have estimates for the truncation error, like how things converge when r goes to infinity, right? We had an estimate on the discretization error with respect to the shifts b, okay? and then we also have an error in this kernel polynomial method, this method involving Chebyshev expansions. And so one of the main kind of approach to numerical analysis is when you look at a problem and you try to get some estimate for all the sources of error, right? And then you try to optimize your method. And optimizing your method means you have several parameters. So here we have r, right? We have number of, R is the cutoff radius, N is the number of discretization points, P is the order of the kernel polynomial method, and then you say, I want to optimize my method. And so if you could set it up as a real optimization problem, which says, well, that was what we did in fact. You take, okay, I say, I want to minimize the total error subject to the constraint of the amount of a kind of computational work. And that means number of matrix vector products, things like that. So you can set it up as a formal optimization problem. The answer is always the case that you want to choose the various numerical parameters so that each of these errors has comparable size. Because remember, if one source of error is minuscule, don't spend all your work making that better. If there's a big source of error, right, then work on that. Okay, you know, a lot of times people spend all their effort on something that's already small. So So the idea is to equilibrate the error. Okay, and so if you balance the error, we end up getting an estimate that tells us essentially the scaling of how the cutoff radius, the number of discretization points, and the iterative solution method. This says, okay, how do these all scale? That's what we've been able to do. Okay, so with all this, okay, so here we've got, right, we just have graphs showing, this is just relative error versus P, where P is where all the other degrees of freedom are taken to balance the error. So that just shows, again, we have a kind of a fast method. And okay, now here's just some of the, let me just talk to you about some of the results. So here, right, so if you look at the density of states for monolayer, that's this red. And the density of states for bilayer, you have these little singularities. That's when the two Dirac. So remember, we have a bilayer. Remember, in a single layer, we had a Dirac cone, and now when we have a bilayer, we have another Dirac cone kind of shifted, and so that where they kind of conically converge, you get a singularity. Well, that's what this is. Okay, now this is something I really like, and this is where I think our method really kind of beats anything out there. So what this is saying, okay, we're scanning the twist, the twist angle. We have a graphene, and then we have another layer of graphene, and we can twist, and we want to study the density of states as that angle continuously varies. Okay, so since our method is very fast, we can actually scan, right? We can actually scan the twist angles, and for each twist angle, we can then compute the density of states. This is energy, and the height, of course, is the density. So we can do this kind of quick study of all the possible design parameters in a bilayer graphene. Okay, and we can also study. This just shows you like local density of states as we right. These are so different. These are different angles of twist: 0.88, 1.11, 1.88, 3.1, and this just this is your okay. So what do we have here? This is okay. So what we see here is each line represents A, B, AA. That says that when the AB, that's the local configuration where the B atom is sitting on top of the A atom, and the AA is where the A atom sits on the A atom. So this just is a way to kind of represent the local density of states as we move through the configuration. Okay, that's what that is. And this is another example similar to that. Okay, so let me kind of mention for those who want to follow up on some of this. So most of what I'm describing is coming out of this paper here and published in SciEm MMS. Okay, some related stuff that's more related to I'm going to talk about tomorrow on Kubo formula for transport. That was published here in Journal of Math Physics. I may say something. Another way to approach all this is through another set of degrees of freedom Okay, so we had real space, we have configuration space. We could also represent everything in momentum space. Okay, and that has some real nice, that's actually the most efficient method of all for reasons I'll tell you about. And then this is a paper, this is where my lecture this afternoon at 4 p.m. I'll talk about mechanical properties of bilayer structures. So if you're a little mystified by electronic stuff, then this kind of gets you more into mechanics. That's at 4 p.m. today. And then what we try to do is, being a mathematician, we're interested in trying to get our ideas and work out there in the physics community, in material science, get it kind of out there. So we have also kind of parallel papers that try to give a kind of a physicsy applications kind of picture of what we do. So this paper here, Twistronics, kind of introduces this this kind of approach I just got through describing through local configuration into the physics community. This has been actually this word Twistronics seems to have entered the vocabulary. So that's, you can always throw on a tronics to something, and it kind of, yeah, that stuck. Okay, so then here, this is this relaxation that I'll talk about this afternoon that gives some very nice applications. And then here, this is a paper that's going to appear in Nature of Materials. And this is where our work is actually compared to really experimental diffraction and dark field imaging work. So that's appearing there. So I think I'll stop there. Thank you very much.
We have time for some questions? Yes?
So you use the fact that it's localized, right? The Hamiltonian is localized.
That's right.
What about cases where it's not?
If it's not, then I mean, we're really taking advantage of the efficiency of the localization. If it's not, then I don't see anything other than just brute force, diagonalizing a gigantic matrix, which is, yeah, that's all I can do. Here, because of the localization, remember, so what we can do is you can either, here's your matrix, you could either take a gigantic matrix, brute force, right? That's the real problem. And so what we're saying is, no, we can actually go and do we can go to some little points we can go around there, we go to all these different points, and we can actually, instead of R being 10,000, we can go and take R equal to 100 and sample 100 points and solve small problems. So that's what localization is getting us.
Further questions? Okay, let's thank Mitch Luskin again. And the next lecture